All right, guys, we're going to try to get through chapter 17. Some of the slides at the end are extra. Obviously, a lot of this is just going to kind of be extra right now, but it's cool. A lot of the stuff at the end is about the heart and reading heart rhythms, and so that's kind of neat. And then the rest of this chapter is kind of interesting as well because of electric circuits. So we are kind of starting into circuits. So here we go. Okay, chapter 17. Who thought? Okay, so this chapter is about current and resistance. Okay, and it's our last chapter before we really start circuits. Okay, so current, we sort of look at current as a flow of electrons. It's not quite as simple as we kind of make it out to be, but our models work really well, and it's nice to not be so complicated. Okay, so looking at the flow of electrons is kind of how you look at a circuit or your computer circuit board. Okay, so current is the rate at which a charge flows through a surface. So if you think of a wire, it's how fast the electrons are flowing through. Okay, there is the definition of average current is charge over time, which leads us to the SI unit of current, which is ampere, capital A, and it's a coulomb per second. Okay, again, all of the stuff in electricity is capital letters. If you want to look at instantaneous, obviously it's calculus, so current is equal to the limit of the average current, which is how fast it's moving in an infinitesimally small amount of time. If the current is steady, then the average and instantaneous currents are the same. So it's kind of like with velocity, if it's a constant velocity, the average and instantaneous are the same. Okay? All right, so here we go. The direction of the current is actually the direction the positive charge will go. Okay? So the flow of electrons on a wire would be this way, but the current is this way, which is why when we draw it coming out of a battery, we always draw from the positive to the negative. So the current will always come out of the longer side of the battery symbol. Okay? All right, so then we get to power. Power is work over time. Okay? There's also other ways to do it. Okay? Here's some interesting ideas here. So in a conductor carrying a current, the potential of the charges is continually decreasing, okay? Which kind of makes sense because it's moving to higher potential. And you're using up battery life, like in your phone, okay? Positive charges move from regions of high potential to regions of low. Negative charges do the opposite. And then power in a circuit is energy divided by time. Okay. We're not going to worry about this, but this comes into account when you start building circuits and trying to figure out how close and far away and timing and all that good stuff. Okay. So we don't usually cover this, but there you go. And this is kind of important here. So if you have a conductor, a wire by itself, we assume that the electrons are randomly in motion, okay? But when there's an electric field there, then we can predict the direction, okay? So here you go, random motion, and there you go, all right? Please don't worry about this stuff. We're trying to hit the basics here so you get an idea here. So in a circuit, so we're talking about something that has a power source and some sort of capacitor or resistor or something, light bulb, something. When you turn a switch on, say in your house, okay, the electrons don't travel from the switch to the bulb. They travel from the power source to the bulb. The switch just cuts the path, okay? Don't worry about drift speed. All right, so circuit, we sort of did this last chapter with the capacitance. So a circuit is a closed path that electrons can flow, okay? And we started talking about circuit diagrams, okay? Generally, you're going to need to know current, also potential, so your voltage, okay? If you notice here, we have a set of batteries that are connected to a light bulb, and that flows back around, okay? This is how you would measure current and potential in a circuit. So if you wanted to measure potential, okay, you have to measure it in parallel. And that's because in parallel, the voltage equals. So I'm going to grab my little handy dandy card. And if you remember from my, I always do this backwards, handy dandy card, the voltage across anything is the same as in the circuit. So if I measure voltage in parallel, then I'm going to get the right potential. Okay, if I measure it in parallel, I'm not. Or sorry, if I measure it in series, I'm not. Okay, so that's why that's that way. However, when I measure current, I have to measure current in series. Okay, and that's because it's the opposite. All right, so if you notice here, we have a circuit drawn, okay? Here's your battery. Your current's going to come out of the positive end of the battery and go through this light bulb. If I want to measure the potential, the voltage, I have to measure that in parallel. But if I want to measure the current, I have to measure that in series. Okay, so those are the symbols. Voltmeters are V, ammeter is in A. Okay, all right, so that brings us to our friend Ohm. He created Ohm's law, or we named Ohm's law after him. He figured out the idea of resistance, and then he figured out the relationship with resistance, current, and potential. Okay, so Ohm's law, your book writes it this way: R equals V over I. I personally usually do V equals IR, just because, I don't know, that's just it. But they're the same, they're just solved differently. Okay. The unit of resistance is the ohm, okay, and it's this omega, capital Omega symbol. It is volts over amps, okay. Resistance in circuits is a place where the flow of electrons is constricted in order to do something. So, like, if I needed to control the potential or the current after a resistor, I would put one in. Or you could think of them as light bulbs as well, where I use that potential that was lost to create light and heat. Okay, so Ohm's law works very well. V equals IR, there you go. We're going to add that to the card. Okay, things that follow Ohm's law are called ohmic. Things that don't are non-ohmic. Okay, if you notice, the slope of resistance here is positive. Okay, in a non-ohmic material, which we are totally not going to worry about, notice we have a non-linear function. Okay, all right, so you're going to work through this worksheet in the second, actually probably the first worksheet of the week. It's a lot like the capacitance one. So this is building the concept of resistance. So resistance is equal to rho, which is a proportion or a constant based on the substance that your wire or your resistor is made out of. L, which is the length of your resistor, and A, which is area. Okay, so you're going to see how that works on the worksheet we're going to do in a little bit. When you increase the temperature in a circuit, resistivity also generally increases. Okay, this is why your computers or your devices have fans in them to cool them off, because if they get too hot, they don't work. And yeah, they can get hot enough to cause a fire, which is what electrical fires are all about. Okay, there's also other ways to cool things off with heat sinks and things like that. And if you're an electrical engineer designing circuits, you have to design them to limit temperature, because if you don't, it's not going to work. Okay, you do not need to worry about this, but this is how resistivity changes with temperature. Okay, there it is again. Please don't stress about it. So this is talking about how energy moves in a circuit. So obviously when you have a battery, you're moving charge and potential, okay? As it moves through a resistor, it loses potential energy because it's being slowed down, okay? All right, so we have a very simple circuit here. Ignore this symbol, it's a grounding symbol. So we have a battery. Notice positive side, negative side. Notice the current comes out of the positive side. And this squiggly line right here is a resistor, okay? I think that's all they're trying to show you there. Okay, here we go. As the charge moves from the resistor, it loses energy in collisions. Energy is transferred to internal energy and then say, I don't know, a light bulb or something like that. Here are your formulas for power. So power is charge over time times potential, or IV, so P equals IV. And then you can also use Ohm's law to make it all those things. So I personally would put all of that on your card, and I will again show you what my card looks like later this week. The SI unit of power is the watt, capital W. And then when you buy electricity from your power company, you buy it in kilowatt hours. And a kilowatt hour is 3.6 times 10 to the 6 joules of energy. Okay, so they're just attaching power, time, and time together. And then this is all the extra stuff at the end of the chapter, talking about some superconductors, which again, that's awesome, but like very limited situations here. So here's more awesome superconducting stuff. They're really neat. And then this part is really awesome as well. So it's electrical activity in the heart. All the muscles in your body, especially your heart, use electricity to pass signals and to contract and relax, okay? The change in potential causes the heart to beat, and some of that is done, well, all of it is done through cell wall and proton pumps and all that good stuff. We can actually attach stickers to your skin, as I'm sure you're aware, to record the changes in potential as your heart beats. Okay, so this is your heart. Up here at the very top of your right atrium is something called the SA node, the sinoatrial node. That is the top of the electrical system in your heart. Okay, so there's sort of like a wire that goes around the top of your heart, and then it goes down the center of your heart, and then right at the bottom of the right atrium, there is what's called the AV node. Okay, and then those wires go into the bottom of your heart. Okay, in a normal heart rhythm, the SA node is what starts your rate. Okay, and generally, I'm going on old knowledge here, but generally your SA node beats between 60 and 80 times per minute. Okay, if something happens to that part of your heart and it's no longer working, the AV node will kick in, and that generally goes 40 to 60 beats per minute, which is just enough to keep you alive. But hey, it's a backup. And then if that part of your heart stops working, the bottom part of your heart, the Purkinje fibers and just the ventricles will themselves beat between 20 and 40 beats per minute. So if you look at an EKG of someone's heart and you see the different rates, you can kind of tell where the damage of their heart is just by that. And then this is your typical heart EKG. Okay, so this P wave right here is your AV node sending a signal, or sorry, your SA node sending the signal. This is where your atrium are beating, and then this is where your ventricles are beating, and then this is the repolarization of your heart. Okay, so we call them PQRST waves. And depending on how far apart they are, where they are, you can tell which direction they are, if they're raised or lowered. You can tell where someone's having a heart attack, especially if you use multiple different leads, then you can kind of see how your heart is responding throughout the heart rate. Okay, so you can see here, they give you one example. When QRS is widened, it could be because you have a large heart. People who have high blood pressure develop enlarged hearts because they have to work so hard to pump against that pressure. If you notice here, we have extra P waves. So something is happening here and we're not getting that conduction through to the bottom of the heart. It can be a problem, but it can just kind of be normal for people too. If you notice here, we're not getting a regular rhythm. There are really no P waves here, okay? So this is telling you that the bottom of the heart is what's really happening, that the top is not working real well, and that the only thing left is kind of the bottom part of the heart. Not a real good sign. Probably a person would need like a pacemaker or something like this to solve it. Which brings you to the next situation here. So now with awesome technology that we have now, we can implant defibrillators, which basically send a strong impulse to the heart, kind of like, when you see on Grey's Anatomy, the paddles. But this sends a little bit less because obviously you don't have to go through your skin and it's going right to where it needs to go. So it will automatically detect a heart rhythm that is not okay, and it will automatically send the shock to the correct part of the heart to get it back to where it needs to be going. Okay, a pacemaker is sort of the same. It's implanted in the same place, but it's usually much higher up in the heart, and the pacemaker only detects rate. So if your rate falls down, or I guess to some degree goes too high, but that doesn't really work so well. So if your heart rate goes down too low, because the top part of your heart isn't working quite right, the pacemaker will send that electrical signal and moderate the rate of your heart to something that's safe. Okay. So again, these devices monitor heart rates on their own. And then when you go to the doctor, they can actually download the data and then reprogram it if you need a rate change or if something needs to be changed. Okay. They work very well, and I think they only have to be changed about once every 10 years now. And that's everything in chapter 17. Hope you guys are doing well. Hang in there. We're almost done.